Welcome back, good people of Cornwall. This is Cornwall's Science Sessions, your weekly science show here on the Source FM. Of course, I hope by now you know exactly what this is. You've tuned in just for it, I'm sure. Right, today I've got some, rather sad news, I'm afraid. Dear friend Sam, co-presenter, he's on holiday. Yes, that means it's just me, all on my own. Just give you a moment to set that in. I know. Dreadful. I mean, how can Sam possibly just leave me? I don't know. Anyway, don't worry, because I've actually got an AI reconstruction of him with me here in the studio. I think it works pretty well. I'm going to call him Sam 2.0. How you doing, Sam? You right?
I'm from London, mate.
No, Sam, come on, we've talked about this. Come on.
You eat me liver?
That's better, mate. Okay. Right, let's get on with the science today then. Got some really cool stuff for you today, actually. First up, we're going to be talking to a very good friend of mine. This chap is awesome. Dr Paweł Sierociński from the Environment and Sustainability Institute on the University of Exeter's Penryn campus, right here in Penryn. So that's awesome. He's going to be talking to us today about bacterial communities. Now, this sounds a bit strange, but essentially what he's interested in is what happens if you take two entirely separate communities, or more than two actually, multiple entirely separate whole communities of microbes and mix them together. It's actually not so simple what happens there. You know, it doesn't just add together in a random fashion. Actually, he's looked into what is actually going on there. And he would be talking about why that matters as well in terms of ecology and also medicine as well. So that's a really cool interview, so stay tuned for that. And then after that, we have another really, really interesting interview with Alice Williams. Now, Alice is a archaeologist, actually, also from the Penryn campus. She's going to be talking to us about something equally awesome, and that is the evolution of settlements in early human evolution. So that's pretty cool. She actually uses simulations for this, so imagine she kind of... Well, it's almost like games she runs, I think. She'll be explaining more about that in a minute. So that's great. Stay tuned for that. And then finally, we're going to finish up with a really awesome interview. This was done a while ago now, actually, a few months ago, with Professor Tapas Mallick. Now, Tapas, he runs the Solar Group, essentially, the solar laboratory based on campus. Now, the solar laboratory, that sounds pretty amazingly cool already, right? It's actually renewable energy the group is interested in. So he's going to be talking to us about solar cells and things like that, renewable energy essentially. Very cool stuff. But before we get on with that, I was in a bit of a sentimental mood this morning. Right, Sam's not here. I thought, you know what? I kind of fancy a bit of a love song special today. So that's exactly what I've got for you, folks. So if you've got any requests, get them to me. Find me on Facebook. Just go on Facebook, type in Cornwall Science Sessions. You can find me there. Send me a cheeky message. Or you can text into the studio, whatever you want to do. Get your requests to me. It's, you definitely need to do that. But I found this in my searching for love songs this morning. I found this. This is awesome, right? So this is a male koala mating call. Just give this a listen, right? I don't know if any ladies out there listening to this. Would this work on you? Let's give this a try. I mean, it's pretty sexy, right? Oh God, listen to that. That's awful. So believe it or not, there's actually a paper came out in Current Biology a while ago, leading science journal, about this particular mating call. Actually, what they're interested in is how this male koala, obviously calling to the female koalas, pretty sexy sound, must admit it. Feeling a bit aroused, actually. Don't know if you are as well. No, probably just me. What they were interested in is how this small koala was able to produce this very deep sound, because actually it turns out that the kind of sound that deep should be made by something much larger, something more the sound of an elephant. It's actually got these particular vocal adaptations which allow it to call that low. There's a really pointless fact for you there. So yeah, I thought that was pretty cool. And I also came across this. Now, I can't really vouch for the scientific accuracy of this fact I'm about to give you, I'm afraid. This is a YouTube job, you see. So this is a penguin mating call. I quite like this. Give this a listen. Yep, that's right, ladies and gents. This is what happens when Pingu gets in the mood. Right, and I thought before we continue, I've got a great idea. How about I'm going to give my girlfriend a call now, and let's try these mating calls on her. All right, what do you reckon? Do you think it's going to work? I've probably got. I reckon the koala will probably win. So what I will do is I'm going to leave you with a song now, and I'm going to give her a call. I'm going to play those mating calls to her. See if it works. You know, see if she gets in the mood for romantic talks. Don't know what you're thinking. I'm just talking about romantic talks. Right. So let's kick off then. So we said we got Paweł on the show later. This was actually his request, so I'm going to play that for him now. So Paweł, thanks very much for coming on the show. Here's your request for you, mate. I mean, I personally can't say I'm a particular fan of this song. I mean, well, I'll just put it on, mate. I'll just put it on for you. Enjoy.
Baby, can't you see I'm calling? A guy like you should wear a warning. It's dangerous, I'm falling. There's no escape, I can't wait. I need a hit, baby, give me it. You're dangerous, I'm loving it. Too high, can't come down. Losing my head, spinning round and round. Do you feel me now? We got taste of your lips, I'm on the ride. You're toxic, I'm slipping under. Taste of a poison paradise. I'm addicted to you, don't you know that you're toxic? And I love what you do, don't you know that you're toxic? It's getting late to give you up. I took a sip from my devil's cup. Slowly, it's taking over me. Too high, can't come down. It's in the air and it's all around. Can you feel it now? We got taste of your lips, I'm on the ride. You're toxic, I'm slipping under. Taste of a poison paradise. I'm addicted to you, don't you know that you're toxic? And I love what you do, don't you know that you're toxic? Don't you know that you're toxic? Taste of your lips, I'm on the road. You're toxic, I'm slipping under. Taste of a poison paradise. I'm addicted to you, don't you know that you're toxic? Taste of your lips, I'm on the road. You're toxic, I'm slipping toxic. Taste of a poison paradise. I'm addicted to you, don't you know that you're toxic? Intoxicate me now with your loving now. I think I'm ready now. I think I'm ready now. Intoxicate me now with your loving now. I think I'm ready now.
Well, I would say great stuff, but well, I'm not going to actually. So that was Paweł's request. That's all sorted now. Now I promised you I was going to play these mating calls. Now let's give my girlfriend a ring. Let's see which one of these works. All right. I haven't got really that much, haven't really got many high hopes for this. Let's give it a try anyway. I'm just picking up the phone now, and we'll give her a call. We'll type in a number. She's bound to answer. Okay. Silence at the moment. Oh. Could it be working? Do anything for you?
Hello?
You enjoy that?
Yes, I did, yeah.
Well, I've got this one. Hang on, stay tuned. No, not feeling anything? Feeling a little flustered? Anything like that? No?
No.
No? Nothing? You're not feeling anything? Oh. Well, ladies and gents, nature has let me down today. Neither of those mating calls seem to work. You on the way to work at the moment, are you, Steph?
Yes, I am, yes.
Alright, excellent stuff. You've got a good day ahead of you?
I hope so.
Good stuff. Alright, off to teach the next generation. Good stuff.
Yes, I am.
Okay, well, no, I didn't really go down as I hoped it would, really. I was expecting, well, okay, I tell you what, I'll find some better mating calls. See if they work a bit better. Well, I'll let you go.
Okay, thank you very much.
Bye now. Bye now.
Goodbye.
Bye.
Bye.
Well, that went dreadfully. What on earth? Come on, who wouldn't find that just really arousing? That, especially that koala noise. Come on, let's give that one last listen. This is a male koala. Just listen to that. Can't beat that. Right, that's quite enough of all this madness. Let's move swiftly on then. I realise you've probably tuned in thinking this is a bit of a strange show so far. Okay, well, don't worry. We're now going to move on, get to the professional stuff. Let's talk about the science. This, of course, is a science show. First up then, I promised you an interview with really great chap, Dr Paweł Sierociński from the Environment and Sustainability Institute here on the Cornwall campus, University of Exeter. And he's going to be talking to us about bacterial communities and essentially what happens when you mix these two, or more than two, multiple bacterial communities together, and what that kind of means for ecology. But enough from me, let's hear from Paweł. But I should probably warn you, this is the kind of madness that occurred when I tried to get this interview to start with. Just give this a listen.
Would you step out of the car, man, mister? Put your right hand on your nose and walk the line.
Yep, that's Paweł, ladies and gents. Well, let's hear the interview. Enough from me. Give this a listen. See what you think. Paweł, thank you very much for joining us. Welcome to the show. Good
My
sir.
pleasure.
I guess we could start if you could just outline for us what kind of stuff you're interested in, because you're a bacterial expert, aren't you, essentially?
I am what people call microbiologist, so a person dealing with things that are not quite visible by your naked eye. But what I'm also is an evolutionary biologist and an ecologist, and what I'm mostly interested in how do communities that contain lots of species of bacteria work, and how do they adapt to the novel environments, and how can we use it for our benefit in some industrial processes.
Cool, yeah, because I think you recently put a paper out in you about what happens when you have kind of multiple, because obviously in the natural environment, I guess you have countless kind of webs of bacteria and very complex interactions, but what happens when you take a community and mix it with another community? I think that's essentially what you were looking at in this recent paper, isn't it?
That's exactly what I'm looking at, and to give an example that may be more suitable for people that can imagine only bigger organisms, because bacteria, and I find it complicated
exactly.
to imagine the networks of webs of feeding of bacteria. What I like to use as an example is if we took a whole patch of forest from somewhere in Canada and a whole patch of forest from somewhere in Norway, we find an empty space somewhere in Scotland. I would suggest the Trump golf course maybe. It's empty and would accommodate a nice patch of trees.
Not quite, is it? It's fine.
And you would mix them there and put them together, those two patches, and see what would happen. Would you get the trees from Canada being better adapted to the Scottish conditions, or maybe trees from Norway still being closer in terms of climate to Scotland that would grow there? And of course it would be related to all the animals that live there, to all the fungi in the soil and stuff like that. The problem is, of course, that this type of experiment is extremely expensive, almost impossible to conduct in this kind of setting. But with bacteria, when you think about it, what we take is we take one community of bacteria living in one factory that produces biogas, one community of bacteria that lives in another factory some kilometers away, and these are completely coherent communities, but they are different from each other. And then we mix them in the same bottle, basically making sure that the numbers of bacteria are exactly the same, and we can mix them and we can later look into their DNA and sort of figure out how do those communities change when you mix them. Our results clearly show that if you mix multiple community, it's the better of the communities individually that will start dominating it in a sort of one community wins with everyone else situation.
Let's talk a little bit as well about the organisms that you're using, because these methane producing organisms are pretty strange, aren't they? Probably most people won't have heard of them or come across them really, even though they are.
You mean archaea or in general?
Yes, exactly. Yeah, I mean.
This is something that even some microbiologists that only deal with straightforward bacteria are not very familiar with. And some geeks might know that there are those archaea bacteria, which to an untrained eye look very much like bacteria. They are also unicellular, so one-cell organisms, rather smallish. They live almost everywhere. They are spread through all the environments. However, they have this particular trait: they can live in extreme environments. So most of the things that live in extreme environments are belonging to the archaea. But maybe it's the first look that is very deceiving. The differences between archaea and bacteria are as big as between one bacteria and you or me. It's just that through the microscope they look similar, but genetically the split between bacteria and archaea is the most ancient of the splits in the tree of life. And they evolved in parallel in similar conditions, but took completely different paths. And what I study is the methane-producing communities, so environments that produce methane, so biogas. We use it sometimes in cooking, and it's basically methane produced by bacteria from rotting parts in an environment when there is absolutely no oxygen. And only archaea are capable of converting the last stages of the biomass decomposition into the methane, which is, from ecological point of view of the cycling of the whole global cycle of nutrients, it's absolutely crucial, because all those anaerobic organisms responsible for rotting and decay of our plant material that just sediments bottom of the lake or in the Arctic soils, they would all die out without those methanogens, because the situation is that if methane is not being produced, there will be an accumulation of acetate. In human language, that's vinegar. And basically vinegar is acidic, so all the organisms that live in those environments, because of the accumulation of acetate, would die from the acid poisoning, let's say. The methanogens are capable of taking the acetate and also hydrogen, which is also an inhibitor of metabolism of those organisms, and combine it to produce methane. And the methane as a gas can be later it just diffuses out of the environment, therefore removing this pH stress from the community. And for us, it's not only important because it is a major process on the global scale. For us, it's also important because we know that if we take a community, we feed X different communities the same kind of food, we know that the one that produces more methane is the healthier one, because this is the one that is more robust in removing those toxic metabolites for them, and it's the one that will use their products more efficiently. And this is where our experiment goes. We took 10 different communities, grew them individually, measured how much biogas they produced, and then we mixed all of those 10 communities into one. And what we found was quite fascinating, for me at least. The mixes produced exactly the same methane as the best individual component of those mixes, which means that we had the best community X, and then the mixes produced exactly the same gas as the community X. And then when we extracted the DNA, sequenced it, and looked at the composition of this community, we also found that the community is not only producing, the mix is not only producing as much gas as the best individual community, it also has a very, very similar composition to that best community. So basically, you see that in a community, you get a sort of co-selection of its components. And this is not a straightforward notion in ecology. Actually, when we started our experiment, we were thinking we were going to mix, there will be like best components from each individual community that will find their space, click together, and we will have a sort of hybrid community that probably has a sort of intermediate gas production in terms of comparison to the individual communities. But no, what we found is that clearly one of those communities dominates, and later a couple of other ones play some sort of ancillary role and contribute a small part of it, and some communities are completely extinct from the mix, which means that not a single part of them is visible inside of the mix, except for the species that are ubiquitous in that environment, which means the species that exist in every one of them. Of course, they will be found because they will exist in every one of them, including the mix. But the species that are originally only found in those weaker, let's say, communities, were not found again.
Regardless of what communities you mix, you always end up with the community which is the most productive, essentially. But I think you went into as well why that might be in terms of like vacant niches and things that more tightly knit or whatever.
That so there is a big caveat that we need to stress. We are looking at anaerobic communities that produce methane, and the characteristical part of that ecosystem is that there is very little energy present in it.
Yeah.
We are very efficient at using energy as humans, and all the aerobic organisms are very efficient in using energy, because what we do is we take one part of glucose, we burn it in oxygen, and from that you can produce 38 particles of ATP, which is the energy currency of every organism. When you think about the same for anaerobic organisms, for each particle of glucose, they can only produce 2 ATPs. So that's a massive 19 times less energy from each particle of glucose that they do, because they can't use oxygen. They have to use other methods of dealing with it that are not as energy efficient. And because of that, all the small processes that are sometimes taken up by one organism produce very little energy. And in order to make these processes feasible at all, they sometimes need to transfer their substrates directly from one species to another. And this is something we might be seeing in our experiments. Because the organisms are so tight together, they might not be so good in transferring their substrate to a species that comes from another community, and therefore they select the ones that they already knew because they co-evolve with them.
Almost sort of symbiotic, almost.
Almost symbiotic, more like co-feeding. But yeah, it's always difficult to say where the symbiosis starts and parasitism ends, but they are very similar processes when you look at it. But almost like a symbiotic process.
So it's very tightly knit.
It's very tightly knit connections, and they might be aided by co-evolving together. So it might help that the two organisms spend some time in the same environment, because then small changes in their mutations in their DNA would cause them to fit closer together, and of course the closer fitting would be promoted, so there will be a massive advantage of being closer and closer together.
So coming back to what we were talking about before then, in kind of years gone by, I mean, we knew nothing about what would actually happen if you took this an entire community and mixed it with an entire other community. We've traditionally been always thinking you might have heard of species invasions, essentially, where you have species being introduced to an already existing
there's good reasons for why we didn't look at those kind of processes. One of them is that this kind of process doesn't happen very often in multicellular organisms. We just don't have situation, maybe, barring some weird catastrophes like continental crashes, when all of a sudden you get two continents that were separated joining again. But of course we have never seen such a thing in our scientific lifetime, so it's difficult. And in terms of examining those bacterial communities, we just didn't have the technology till quite recently. What I do to get what's inside of those communities is I take the DNA of each bacteria inside of it, and we sequence a particular gene that is common to all bacterial life, and based on that evolutionary tree of life, I can actually see which species those pieces of DNA belong to, and then I can build the list of species present in my communities and in my mixes. And that was very expensive till just 10 years ago. It was almost only available for massive consortia. I don't know if you remember Human Genome Project some time ago. It costs hundreds of millions of dollars. Now you can achieve the same for mere, thousands, maybe a dozen thousand something like that. So the technology became massively cheaper, and we are actually now in the right position to start tackling those questions.
Yeah, it's great. I mean, as well, it's worth considering actually how vital it is to understand this, right? Because, as you said, doesn't happen in multicellular organisms. We don't see this happening.
Well, it
at our
does
level,
happen to multicellular organisms. It happens in multicellular organisms. When you think about it, as humans, we are roughly 50% our own cells, 50% bacterial cells. We have a rampant group of microbial communities living inside of us, and we think that at least part of this research is going to help people that are dealing with how you manipulate human microbiome, so the bacteria that live in our gut, on our skin, to be more beneficial for us. They will look at those kind of processes, because right now we start looking at fecal transplant, which, as gross as it sounds, it means transplanting a whole microbial community from one person and putting it into another person to improve that person's life. It has been shown to work miracles for some diseases like persistent bacterial infections after surgery, for people that have issues with their health.
Yeah.
Or people that are continuously under antibiotics. They often develop those kind of infections.
Yeah.
And fecal transplantation has shown to be working miracles for those people, with the healing rate of 95%.
Wow.
And I think that looking at the fact that mixes of communities, if you mix multiple community, it's the better of the communities individually that will start dominating it. So if we know that in a therapeutical way, and if it also works in our gut, then we know that for curing these people, it's better to transfer fecal transplant from multiple people than just from one, because you increase your chances of finding the one that will be working fantastically. Sure. Of course, that needs to be verified on the proper human model, because what we can only say right now is that it works in our methane producing communities.
So, awesome stuff. That was Dr Paweł Sierociński from the University of Exeter here in Penryn. Yeah, very interesting. This will, I imagine, cause quite a stir in the science world, this kind of these kind of findings, because essentially what they've shown is that if you mix up, as Paweł was very nicely explaining there, if you mix up multiple communities of microbes, and these communities might be doing something useful. So, for instance, in the human body, of course, we require bacteria in our guts to aid digestion, things like that. And what Paweł was saying, that actually he's finding that if you mix multiple communities together, it's actually usually the most productive, or in other words, the best communities that dominate the kind of resulting mixture of communities, if you like. So what he was saying was that that's actually very relevant in terms of health. And also biotechnology as well, because if you think about producing biogas, and the communities they're actually using in their study were producing biogas, they were methane producing microbes, these strange little archaeobacteria that he was talking about. So they were producing methane that actually is used as biogas, to power, as fuel, essentially. So if they're showing essentially a way of improving efficiency or the productivity of communities inside these reactors creating this methane, then of course that is a very good thing. So I imagine that will that will be causing a stir in days to come, I imagine. So keep your ears peeled. Is that a thing? I'm not sure if that is, but just do it anyway. Right, and we already sorted out Paweł's request. He did, of course, as usual with these academics, they always insist that we play their particular request before they come on the show. His particular request was Toxic by Britney Spears. I think maybe because he works with microbes. Maybe he likes to have this kind of image that a lot of them are toxic, which isn't necessarily true, of course, but that's probably the reason for that particular theme tune. Also, he's just a rampant fan of Britney Spears as well. Anyway, I'm sure we'll hear more from Paweł in shows to come. If you've got any questions, of course, as always, get them to us. I can always get them to Paweł himself as well, and I'm sure he'll be happy to answer any questions that you've got. Right, so let's move on. So at the beginning of the show, I promised you that we would move into talk a little bit about the kind of evolution of early human settlements. So we'll hear from Alice Williams, is an archaeologist here at the University of Exeter. We'll hear from her in a bit about that kind of work. But I realise that you're probably a bit concerned at this point. So it's just past 8 o'clock in the morning. this is time for your weather and travel. But I told you earlier that Sam's not with me. So what are we going to do? Well, don't stress, because actually we're going to give Sam a call in a minute, and he's going to give his travel and weather remotely. You know, a very, very important man, which is good. He's going to give us a call and sort that out. So for now, I'm going to leave you with a cheeky tune. Yeah, this one is awesome. Found it recently. Brad Paisley's the guy, a folk artist. Yeah, just give this a listen. This is a brilliant, brilliant tune. Perfect for the kind of love and breakup songs theme today, of course, because Sam isn't here. Give this a little listen. And when you come back, yes, that's right, Sam will be with us to give us the weather announcement. So do not fret.
Care if people stared. We'd make out in a crowd somewhere. Somebody'd tell us to get a room. It's hard to believe that was me and you. Now we keep saying that we're okay, but I don't want to settle for good, not great. I miss the way that it felt back then. I want to feel that way again. It's been so long that you forget the way I used to kiss your neck.
Remind me.
So on fire, so in love, way back when we couldn't get enough.
Remind me. Remember the airport dropping me off. We were kissing goodbye and we couldn't stop.
I felt bad cause you missed your flight, but that meant we had one more night.
Do you remember how it used to be? We turned out the lights and we didn't just sleep.
Remind me, baby, remind me.
Oh, so on fire, so in love. That look in your eyes that I miss so much.
Remind me, baby, remind me. I wanna feel that way.
Yeah, I wanna hold you close.
Oh, if you still love me, don't just assume I know.
Oh, baby, remind Do you remember the way it felt?
You mean back when we couldn't control ourselves?
Remind me.
Yeah, remind me.
All those things that you used to do that made me fall in love with you. Remind me, oh baby, remind me.
Yeah, you'd wake up in my old t-shirt. All those mornings I was late for work. Remind me,
Oh baby, Oh baby, remind me. Baby, remind
yeah, you'd wake up in my old t-shirt. Baby, remind me.
Sam is on the line. Sam, can you hear us?
Hi Ben.
Hello, mate. How are you doing?
I'm doing all right. How are you doing?
Fine, thank you. Yes, it's
Show's sounding great, by the way. You don't need me.
Oh, mate, we certainly do need you. Have you not heard it's taken a bit of a turn for the worse, mate? It got a bit too romantic actually earlier. So that's what happens.
Playing the mating calls.
Yeah.
Radio.
In your absence, mate, it goes all horribly wrong. So I'm sure next week the listeners will be pleased to know it'll be back to more sensible material. But don't worry, mate. I've also got your backing, of course. I don't think you'll hear it through the phone, of course. So what I'll do is I'll give you a countdown, all right? Because it's very important you've got your backing, obviously.
Yeah, obviously.
Okay, right. Well, let's get the backing on for you, mate. Okay, it's currently on.
I know I can hear it.
Oh, you can hear it. Brilliant. Even better. All right. Well, I'll leave it to you then, mate.
See,
Bet it sounds even better through the telephone, mate.
and that's just
I've
in the
ever wanted.
studio. Weather and travel. Take it away, Sam.
All right.
Alright, so your weather updates today are that the skies will generally be rather cloudy, perhaps with the odd shower at times. However, there'll also be some bright spells around too, particularly later in the afternoon. You'll have maximum temperatures of around 15 degrees, but it could be cold when it turns breezy. Moving on to travel, we have queuing traffic on the A39 in Toulouse, in Penryn, and we also have queuing traffic on the A90 in Highertown near Truro. The A390 in 3 Milestone is usually very slow traffic, and the travel time is roughly 10 minutes. And also expect heavier traffic than normal at the A390 in Truro as well, up by Highertown. Everything else seems relatively okay, so yeah, not too
Awesome.
much to worry about this week.
Brilliant. Well, thank you, Sam. I hear you've got a request as well. Some Puff Daddy. Is that right?
I do. I've requested some P Diddy or Puff Daddy, whatever you prefer. I'll be missing you, Ben.
Oh, excellent, mate. Oh, just be careful, mate. You don't want me to get in a more romantic mood than I already am. So, well, in that case, mate, I might just have to play that next for you. How about
Thank you
that?
very much.
Okay, well, cheers, Sam. I'll see you soon, sir.
Thanks up, Ben. Keep it up. It's going well.
Thank you, mate. Goodbye now, sir. Bye now.
Goodbye.
Right, great stuff. Of course, that was Sam, the weatherman, the unbeatable weatherman. Yeah, and I wasn't lying when I said up next is some Puff Daddy. Yes, it's Puff Daddy. Let's give that a little listen. I already know this is a great track. Of course, everyone knows it's a great track. Who doesn't know this is a great track? Let's get it on. Come on, let's get this.
This right here, tell me what goes out to everyone that has lost someone that they truly love. Come on, check it out. Seems like yesterday we used to rock the show. I laced the track, you locked the flow. So far from hanging on the block for dough. Notorious, they got to know that life ain't always what it seemed to be. Words can't express what you mean to me. Even though you're gone, we still a team. Through your family, I'll fulfill your dreams. In the future, can't wait to see if you open up the gates for me. Reminisce sometime, the night they took my friend. Try to black it out, but it plays again. When it's real, feeling's hard to conceal. Can't imagine all the pain I feel. Give anything to hear half your breath. I know you're still living your life after death.
Every move I make, every single day, every time I pray, I'll be missing you. Thinking of the day when you went away. What a life to take, what a bond to break. I'll be missing you.
It's kinda hard with you not around. Know you in heaven smiling down, watching us while we pray for you. Every day we pray for you, till the day we meet again. In my heart is where I keep you, friend. Memories give me the strength I need to proceed, strength I need to believe. My thoughts big, I just can't define. Wish I could turn back the hands of time. us in the six, shop for new clothes and kicks. You and me taking flicks, making hits, stages they receive you on. Still can't believe you gone. Give anything to hear half your breath. I know you still living your life after death.
Every move I make, every single day, every time I pray, I'll be missing you. Thinking of the day when you went away. What a life to take, what a bond to break. I'll be missing you. Somebody tell me why. One bad morning, when this life is over, I know I'll see your face.
Every night I pray, every step I take, every move I make, every single day, every night I pray.
Every day that passes is a day that I get closer to seeing you again. We miss you, babe, and we won't stop, cause we can't stop. That's right. We miss you, babe.
Every step I take, every move I make, every single day, every time I pray, I'll be missing you. Thinking of the day when you went away. What a life to take, what a bond to break. I'll be missing you. Every step I take, every move I make, every single day, every time I pray, I'll be missing you. I'll be missing you. Thinking of the day, when you went away. What a life to take, what a bond to break. I'll be missing you. Every step I take, every move I make, every single day, every time I pray, I'll be missing your face. Thinking of the day.
Well, great stuff. Great stuff. An excellent request there from Sam. Good job, sir. Right, moving on then. Now, I promised you that we'd soon be chatting to Alice Williams, the archaeologist, who's talking about the evolution of settlements. Very interesting section. So it's in two parts, so don't go anywhere. Hear from the kind of main interview first, and then she's actually going to explain two pictures, two figures that we've got on our Facebook page briefly after that as well. So if you find us on Facebook and you find these pictures, if you listen back to this show, you'll be able to kind of hopefully know what's going on in these pictures to kind of explain the kind of work that she's doing. Anyway, let's hear from Alice now. So this is Alice Williams from the University of Exeter, archaeologist with an interest in the evolution of settlements in early human society. So let's give that stuff a listen now.
I'm an archaeologist. I'm here doing a PhD at the moment, and I'm trying to work out why societies formed the way they did. So why did we go from small villages right the way through to states and kingdoms and empires, and because that's not an inevitable thing to happen. So I'm looking at the archaeological record, and I'm also building simulations to try and test some of our assumptions about the archaeological record in sort of a separate lab almost, and see if anything works or not.
Yeah, that sounds awesome. I did actually attend a talk that you gave a while ago with one of these example simulations in. Essentially, I guess you set the rules for these. Essentially, they're like games, I guess, right? You set these rules for the simulation, and then you just let it run, and then I guess that's how it works. I mean, I've got no experience at all with anything like that. I'm a lab-based man myself. So.
Yes. Well, absolutely. Well, the key there is it's very easy to get sucked into this idea of trying to replicate reality in a game, and then you end up with something that's not actually useful. The point of the model is to try and simplify reality into a certain way so that you can test an assumption, a specific assumption, rather than just replicating everything you can possibly think of, because then you get lost in all the parameters and all the numbers, and it's very hard to find anything meaningful from it. In my very simple model, because I'm trying to keep it as simple as possible at the moment, I'm trying to get my villagers to weigh up the costs and benefits of either conquering the neighbour, and if they are conquered, to then either stay where they are or move away somewhere else. And so this is, if, for example, if you're a village and you're happily farming your own bit of land somewhere, you then get somebody else come and decide that they want your land as well, and your people, whatever. You then got to think, well, if I stay where I am, I can keep my nice land, but I will probably have to pay some sort of tribute to this sort of dominant village who's conquered me, or like do what they say if they go and conquer somebody else. Or I can go and find a new patch of land somewhere else and set up again and essentially run away and not pay that tribute, not become subordinate to anybody else. But the key thing here that I'm looking at is if that land that you're trying to run away to is worse quality than the land that you're currently on, to what extent will that mean that you're more likely to want to stay put and become subordinate? And therefore, does having sort of worse environment surrounding a certain area mean that people are more likely to want to stay, and that a complex society will form more quickly? So so essentially I've got one village will try and attack another village of its closest neighbour. It then decides, do I want to stay, do I want to go, and so on and so forth.
No, awesome. And I guess then you can, of course, change the rules somewhat to ask different questions about what's most important and things in terms of making that. It's interesting you're saying it's about these kind of trade-offs, because it sounds to me very much like the kind of simulation you're running probably features in science in other places as well.
So what I'm doing is very much just agent-based modelling simulation. Sure. And that type of simulation is where you've got agents within the model who make decisions as they're going along. It's also different to other mathematical types of models that you might see in economics or in biology, because that is very much, there's an answer at the end. You sort of put in your equation, and given this exact sort of settings, then this outcome is expected. Whereas with an agent-based model, you can run the simulation many, many times and never get exactly the same result, because each time it'll sort of start off with different sort of setting point, or different villages will make different decisions, that sort of thing.
Have you got any kind of what are you seeing at the moment in your simulations? Or I guess you might just be simply designing these simulations. I guess that takes ages.
Yes.
But I don't know if you've managed to see anything coming out of these models or anything interesting like that.
Well, getting there. I mean, so the model I've got at the moment is very much still quite abstract. So I've got in there my environmental sort of conditions. So with that, I've got an area of more fertile land, and then the ecological gradient between more and less fertile land and things like that. From these initial results, I can say that there is some effect of having a worse environment on the rate of hierarchy formation, but then that is very much mediated by the level of tribute that would be demanded by a conquering polity, and the level of internal stability of a polity as well. So if a village or a society is really unstable, it will have villages within it that can decide to rebel and move away of their own accord and form their own polities. And if that keeps happening, then obviously hierarchy won't really form, and you'll sort of stay with fairly simple societies. But yeah, so then the next stage after that is to what I'm working on at the moment, introduce a level of more realistic side of the model building, so more population growth. Then eventually I'm going to build the model in such a way that I can compare it more directly with the archaeological record in the Valley of Oaxaca in Mexico. So I'm going to have the environmental conditions based on the sort of fertility of different areas of land in that valley, and then run the model, see if I can vaguely predict when and where different sort of more complex societies form in that valley, and sort of say, does having worse land around an area predict the state formation in this particular part of the world?
Oh, that'd be really cool. So essentially taking these models and feeding in real kind of environmental data from real locations and seeing if you can kind of replicate what's actually gone on.
Yeah.
Yeah, that's really cool. I guess it's you know, as you're very nicely explaining it here, so I think I'm kind of understanding it. But I imagine it's very difficult even to get to a stage where you've even got, I don't know, it working remotely kind of predictably. I would guess a model like this. I guess there's a lot of tweaking parameters and things like that goes on behind the scenes.
I'm very much trying to work out what assumptions there are, because naively at the beginning I thought, oh, I'll just make this model and it will work because it's quite simple, but every single decision has to be thought through, and so many times I've tried to run the model and found that something's doing something I wasn't expecting just because I hadn't thought through the logic of what I was saying enough.
Yeah, sure.
so it's been a lot of going back and editing and making it work.
This kind of thing which you're doing, to me, that kind of sets humans apart from everything else in nature. Because I guess first villages, I've just got a quick note here, 10,000 years ago, I think, roughly, is that right?
Yeah.
And then since then, I guess we've seen this incredible expansion in technology.
The depth of time we're talking about here is obviously immense. I mean, first villages 10,000 years ago, but it's also really not that long compared to even like the start of our species. It's in the whole time that Homo sapiens has existed, I think sort of roughly speaking about 250,000 years ago. That's a really long time for a species to emerge and then to get like beginnings of farming, beginnings of villages, and then even to sort of seeing the nations and states that we take for granted today. That's really, really recent. So it's really interesting to see just how quickly we can change. And I think one thing I really like about humans is it's not so much that we have states that we can see now, but that we have this ability to adapt to whatever environment we end up in or create ourselves. And that's amazing when you see sort of across the whole world how very many different societies there are and how people behave so differently, and yet they're all people and they all behave just as people do.
That's a nice thought, actually. That's Alice Williams, ladies and gents. Don't go anywhere. She is coming back. She's going to explain, actually, a couple of figures that she sent to us to hopefully give you a better understanding of exactly what she's actually talking about here when she talks about these simulations, essentially like mini games that she's made, basically, that she uses to try and work out a little bit more about what was going on in this kind of early stage when villages were just kind of first forming, and how these villages essentially become whole, entire and very complex huge societies, huge hierarchies of different kind of settlement types. So do stay tuned for that. But first, I've got something very exciting for you. This is a song. It's called Follow the River. It was actually written and recorded by our very own Mr. Sudan Wang. Now, Sudan is from the University of Exeter's Environment and Sustainability Institute. So, Sudan, if you're listening, this is a great track, mate. Very pleased to be playing this today. It also features Mr. Sam Barton. Sam is a very good friend, of course. Listen out for him. You'll hear him about 3/4 of the way through the song. You'll hear him. Give this a listen. Brilliant singer. And, well, don't even need to say much else, really. Play this again, I'm sure, at some point. We've also got two versions, actually, I should say. This version is the kind of full-blown version, and there's a much more romantic late-night version. So who knows? Maybe we could finish the show with that one. Well, for now, let's give this a listen. Do try not to get too emotional. If you're driving, please take this easy. Maybe drop the volume a bit. Get your tissues ready. Okay, ladies and gents, here it is, Mr. Sudan Wang and Follow the River.
Follow the river down to the sea, to the old harbor, sleepy cornerstone. Where shall I be? My good friends and me. The way the beat love to raise Cause love songs in time of dreams， 这是我们的家，这是我们的家，这是我们的家，这是我们的家。那个女人 Follow that river down to the sea, so that old sleepy coast town will share a beer. My good friends and me, they hit the beat to record our tune. Oh.
Now that really is great stuff. I know I say great stuff a lot, but that truly is awesome. Great song, Sidan Wang singing there. Song called Follow the River. Awesome stuff. Right, well, let's move on with the science then. So we heard, just before that song, we heard from Alice Williams talking about the evolution of society, essentially, the evolution of, all the way from villages up until very complex and much larger hierarchies of different types of settlements. She's now going to come back now and talk a little bit more about that. She's actually explaining two figures which she's sent to us. So if you find our Facebook page, Cornwall Science Sessions, you'll be able to check those images out and maybe listen back to this show on there as well. And if you're interested, hopefully you'll be able to get a better idea of the kind of simulations she was talking about, because of course she can't go back in time and see these societies and actually see how they're kind of working and how they're evolving. So of course she simulates them in these models that she makes. So let's hear her now talking a little bit more about that, explaining these figures. Let's give this a listen.
I've got two images I'll send to you. One of
the
awesome. model itself, and then one of the area that I'm looking at in Mexico.
Oh,
so
lovely. Okay.
Can show that. So with the picture I've got of the place in Mexico, it's of the capital city, Monte Alban, and you can sort of see in the background there's some mountains, which I'm assuming for the purposes of this model are the land that is really hard to move into. So it's quite an amazing place. It's very, very flat valley floor and then just walls of mountain on all sides. And in this place, you've got this settlement called Monte Alban, which formed and became the largest settlement in all of Mesoamerica at the time. And which, by our standards, is very small. They had a population of about 5,000 people, but this is pretty good compared to when you've only had villages before that. And you can see from that picture, it's got a plaza which had been artificially flattened, and all these temples built to have the population there, and sort of, I don't know, it's just really complex. It's the first most really complex place there.
Right, great stuff. Alice Williams, that was, ladies and gents. Again, go on our Facebook page if you want to see a little bit more about that. She sent us two of the figures which kind of accompany her research, so check that out. Right, okay, in terms of the science, we've got one more awesome feature left for you. We've actually got an interview with Professor Tapas Mallick. Now, this was done, a few months ago now, but it's still awesome, and it's actually, I thought I'd play it today, especially because we've almost covered a little bit about it. Well, we were talking about biogas earlier with Dr Paweł Sierociński, but in that sense we were talking about what happens when you mix up these different communities of microbes, and actually he was talking about his recent paper, which is soon to be published in Current Biology, so congratulations to Paweł for that. But he was talking about what happens when you mix up different communities. So in the sense of, in the case of methane producing microbes, of course, he basically showed that if you mix up a bunch of these communities all producing methane, it's usually the best, and what he means by the best, the most productive. So the communities producing the most methane almost, those communities actually end up dominant in the mixture of communities. So one way to kind of get a more efficient methane producing community could be to mix up a bunch of communities, because then obviously only the best will then become dominant and the others kind of play a little bit of a kind of helping role, Paweł was saying. So we're kind of talking a little bit about biogas and the production of biogas. This is kind of more, let's move into the kind of more kind of hardcore renewable energy now. And this is Tapas Mallick he's a professor here at the University of Exeter at the Solar Group, and he's talking about solar energy, which is of course a renewable energy source. He's talking about what kind of things this kind of field is currently facing. What to think about when we think solar energy. Where is it up to? What kind of work is being done in that field at the moment? So let's listen to that now. Let us know what you think. This is Tapas Mallick, ladies and gents. So thanks very much, Tapas, for appearing on the show. Now this week we've got Professor Tapas Mallick here. He's the Chair of Clean Technologies here at the Environment and Sustainability Institute, and he's the lead of the Renewable Energy Group here in the College of Engineering, Maths and Physical Sciences. So Professor Mallick, could you talk us through the kind of technologies that you're interested in here?
Hello, thank you very much for inviting me this particular sessions, and it sounds like an amazing thing to do. I particularly work on the solar technologies, making the solar systems more cheaper way and more affordable way to provide the electricity for general publics. That doesn't necessarily mean that we need to have more and more large-scale solar farms and replacing the agriculture field, but rather than how the solar technology can go into the every single household and implement in a better way such that the electricity can be provided to the all common people. So and surrounding to those particular solar technologies, we do research on the new materials, how we can even get better and much more efficient solar technologies. And then we work on the device, which is like very much simple, like experimental side. We do a lot of laboratory research and experimentations, and then we do the other thing, which we call it, scientists call it, system level engineering and research challenges, which is goes to a real time. For example, in households or every residential houses or even in the roofs, and we do a lot of research surrounding that. So essentially, we our research spans over various fields, from the very fundamental materials to the large-scale systems and their implementations, and how best we can provide the electricity to the common people, I suppose.
Cool. So I guess it's really then the main challenge currently is presumably their costs then of the solar cells themselves.
Yeah, I think that there is two things. One is the cost of the systems, and another thing is what is the efficiencies. And efficiency means, in a very simple term, is how much we are putting in and how much we are getting out of it. So essentially, I mean, if you get a better and efficient cells or efficient solar technology, that directly reflect to the cost element of it, which essentially means that affordability of the solar technologies goes very wide, and also the cost of electricity, which you get very much after a certain period of time, is free. It would be even longer period of time you'll have the free electricities. So essentially, in other words, that means your electricity bills is going to be less and less, and you will have one can enjoy the free electricity for longer period of time.
Great. So I'd also like to ask a question about the actual science behind the solar cells, if you don't mind. So I think the way that I understand it works is that it's literally capturing the energy of the sun's rays in the form of the motion of charged particles. But I can think of another system in biology, actually, that I'm more used to, that works in a similar way by capturing the energy of the movement of electrons, and that's photosynthesis. Are there any kind of parallels between those two systems, or is it really completely different?
Oh, that's very, very interesting questions. Yes, it is. In fact, in some of the technologies we do, what we call it artificial photosynthesis, we do the exactly similar things. So essentially, in the solar cell technologies, what happens is as soon as the sunlight falls into this particular surface or some particular type of materials, what they does is they create some particles, positive charged particles and negative charged particles. And then if you can think, if we just pull them separately, those two charged particles in two different directions, and if we have some kind of load, which is essentially our bulbs or electrical bulbs, and if we can separate those charged particles towards those full circuit, then essentially we get the electricity. And that is the very fundamental principles of the solar technologies or solar cells. How does it work? Now, surrounding that, there is a lot of engineering and scientific challenges, is how best we can separate those positive and negative charges. Obviously, as you can imagine, that always positive and negative charges, they will always try to combine together very enhanced way. So we need to separate them in a extensive way, and that comes back to your science and the engineering challenges, what is called the material band gap, which is how far they can go, how far they can stay, and so on and so forth. So I'm not going to go through in detail on that, but it operates in the similar principles that photosynthesis or charged particle motions happens. Now, the similarity in another words is there, which is called artificial photosynthesis, where you generate hydrogens in presence of sunlight. So if you have a particular material which goes into the water, and in presence of sunlight, exactly similar sort of things happens, but in a reverse way, so that instead of getting carbohydrate, you get the hydrogens and oxygens. And we do have a fantastic research in ESI itself looking at those challenges. Again, the key concern, which is like how best we can get more and more hydrogens out of those systems, is a big challenge. So material, working with the materials in a various scale, even in the nanoscale, for example. I mean, nanoscale is 1 millionth of a hair. I mean, if you can think about that scale. So in a very tiny little scale, we need to work on that to tune the materials accordingly, so that we can get the best out of this whole thing.
So, Professor Mallick, thanks for that. So, other than solar cells, do you think there are any other technologies which would be able to benefit us in the future?
What I think is in this energy spectrum, energy mix is a very good thing. I mean, good thing in the way that energy mix need to be there. So it cannot be, I cannot just claim that the solar itself will solve the whole problem. So it's need to be mix of different energy technologies. For example, solar, for example, biomass, for example, marine technologies, all the renewables, including there are several activities in the other clean technologies. So it has to come from all different spectrum, and it's, in a sense, I think that doesn't mean that we'll be replacing the fossil fuel completely. We cannot do that. We need to have a dependencies on the fossil fuels also. But the longer we have contributions from the other clean technologies, the longer and longer we can survive, or we can be dependent on the fossil fuels. So essentially, the replacement, 100% replacement of fossil fuels, I don't think it is going to happen in the next 5 or 10 years. But certainly, you can see more energy mix will be happening every single day, I think, to match the energy demand we have in the whole spectrum, I suppose.
Cool, thanks for that. Well, I've heard some people saying that the kind of holy grail of clean energy, if we could manage it, would be nuclear fusion, the process that powers the sun. Do you see any future at all in that, and how far have we actually come in that area?
Yeah, well, I mean, there are. It's again an interesting question. There are a lot of discussions on nuclear fusion, but there are too many challenges at present time. Obviously, the safety is a big concern, and then the affordabilities and reliabilities of the technologies. And to my mind, I think we are not anywhere near in that particular areas that the common people should be, or people like us should be too confident that it is going to be the future of our energy supply. But then again, I mean, we don't know what's going to happen in 50 years' time, but what we can understand, or we know, that sun never is going to disappear even in 50 years' time. So I think it will be there as long as we will be there. So I think it has to be. So whatever the technologies you are talking about, I think solar always would be a key contributor to our human life, I suppose. That's the way I can think of it.
That sounds good. Well, thank you very much for that, Professor Mallick. And we've also got a visiting professor with us here today. Would you like to introduce yourself and say a bit about what you're here to do?
My name is K.S. Reddy. I am from IIT, Indian Institute of Technology, Madras, Chennai, in India. I am a professor in mechanical engineering. We work on renewables, power generation, and heat transfer related areas of research.
So, are you here to work with Professor Mallick on solar cells, or is that what?
Yeah, I work with Professor Mallick on renewables, mainly solar cells, and these cells are more efficient cells, which are of triple junction solar cells, concentrating solar cells, where the concentration of solar energy makes these cells to work at a very high efficiency. Apart from electricity generation, we get some heat out of that. That heat can be used for space conditioning, mainly for buildings and other places, and desalination, or potable water production, as well as the air conditioning.
Oh wow! Okay, yeah, no, that sounds very cool. So, question to both of you, really, open floor now. What do you think are the kind of most exciting current progress or breakthroughs or whatever currently in your areas?
I think the high efficiency solar cells. I mean, we have now in the world 47% efficient solar cells. It's been recorded by scientists from Germany. So I think the 50% solar cells would be not far away. So I think within the next couple of years, I'm pretty sure that one can see the 50% efficient solar cells.
And that sounds like a vast improvement on what it's previously been.
That's been vast improvement from what's been demonstrated so far. And surrounding that, I think the collaborative research we have, particularly with Indian Institute of Technology, Madras, and my colleague is here, and surrounding the heat transfer problem or heat related problem from those cells is enormous and big challenge. So I think effective heat recovery or how to use the waste heat and in an effective way, I think even though both including the thermal and electrical, I'm pretty sure, I think Professor Reddy would be agreed that we'll see something like 70-75% energy recovery from the cells.
Well, gentlemen, thank you so much for speaking to me, Professor Mallick.
Thank you.
Thank you very much, sir.
Thank you.
And I'm sure we'll catch up with you soon. So, thanks very much again to Professor Tapas Mallick for doing that interview. As I said, that's a few months old, that particular interview is, but I think it's very relevant now. It's always very relevant, this kind of push for renewables, renewable energy. And as well, another point to make there is really interesting to see that he had this visiting professor with him on this particular day of the interview. And to me, that just is great, because it just shows really how interdisciplinary science is, and the fact that you just need these collaborations across countries. Awesome. Nice to think that we're all working together. Awesome stuff. Right, okie dokie. Before I carry on, so we're coming to the end of the show now, so I'll play some beats for you, actually. If you've got any requests, get them to me. Of course, well, yeah, I mean, I've got a song I'm going to have to play, dedicated to Tapas. This one is High Voltage, obviously. That'll be coming on shortly. I just wanted to give you a quick announcement, actually, about some courses the University of Exeter are running. So I'll just read you out this flyer. So it's called Return to Learning, and it's basically a series of workshops coming up in May and June, about skills that you might require to actually return to learning in higher education. So let me just read this out for you in case you're interested. So the University of Exeter will run a range of workshops that have a focus on developing skills for people looking to return to education, giving practical advice and guidance. These workshops look at developing practical skills, such as what skills you have and what you need to be a student, and structuring academic learning. You will explore options and possibilities within Cornwall and find out about funded short course accredited opportunities. You'll be able to speak with some of our mature students and explore the funding and finance side involved with higher education. So, if you're interested at all, get in touch with, here's the person to contact, Charlotte Bailey, and you can call her on the telephone, so that's 01326 370 412. So that's Charlotte Bailey on 01326 370 412. Or you can email c.bailey@exeter.ac.uk to book your online places. They're also on Eventbrite if you find the Return to Learning free skills workshops. So again, that's just about if you're remotely interested in returning to learning, these are free workshops which are being put on by the University of Exeter to kind of give you some more ideas about that, and also about the how to go about funding them as well. So check that out. Anyway, that's actually come to the end of all the serious stuff for you today. So thanks again to everyone who appeared on today's show. So we had earlier, right at the beginning, we spoke to Dr Paweł Sierociński on his work on microbial communities and what happens when you mix up microbial communities. And we spoke as well on kind of what that means for things like biotechnology. So we spoke about biogas, for instance, these methane-producing communities, and how to make these communities more productive, essentially by mixing up lots of different communities. And also we talked a little bit about health as well. So this fecal transplant stuff, which of course sounds a little bit disgusting, but actually, as Paweł explained, it seems to be a very promising area in medicine. And of course, research like Paweł's is actually essential to better understand that and even improve it. Then we heard from Alice Williams, who's an archaeologist at the University of Exeter as well. She was talking about the evolution of human settlements, essentially. So, how did humans go from starting out with just these small villages, and how did that turn into huge, very complex entire societies over time? Huge hierarchies of different settlements. So she spoke about that. So if you want to hear either of those two, again, just find us on Facebook. I'll post the podcast on there, so you can catch up with that. And of course, just then we heard from Professor Tapas Mallick in one of these. This is an older interview, actually, a few months old, as I explained, about solar energy. And of course, he had the visiting professor with him at that point as well. So any of that, if you want to hear any of that again, do find our Facebook. Just search for Cornwall's Science Sessions. And even if the only reason you tune in is just to hear the mating calls at the beginning, I don't mind. I'm not going to be angry with you. Tune in just to hear the mating calls if you want. So that's about it in terms of the science. I'm going to finish up now with a couple of songs. Now, I told you that the theme for today was love and breakup songs, all because my dear co-presenter Sam, he left me.
All by myself.
I know it's hard to believe, but don't worry, he will be back next week. He did, of course, tune in today to with weather, which was awesome. Thanks, Sam. So do tune in for that again. If you missed it at the beginning of the show, I would just like to remind you about this. This is a male koala doing a mating call, calling out to all his females. Pretty gross, actually. This call. Give this a listen. Yeah, I don't really want to imagine kind of what's going on at this point. Oh no, this is the worst bit. I'm pretty sure I can do a good job of that koala mating call, actually. I don't know, what do you think? Rate this out of 10. Yeah, I think that's probably about 11. Anyway, let's not talk about that again. That was a dreadful start to the show. I do apologise. Won't happen again. Right, let's play some tunes then. So I think, as I promised, I'll start out with High Voltage. Now, I think this should probably be Professor Mallick's theme tune, because, of course, he does work on renewable energy. So here it is, Professor Mallick's theme tune. Right, okay, that was Professor Mallick's theme tune, I think. Yeah, so now let's... Oh, what's going on? Oh, no. No, not the haunted telephone. Oh, no. I think the haunted telephone... No, what's it doing? I can see it. What's it doing? No! What's it doing? Oh, this is spooky. I warned you last time, ladies and gentlemen. I think the telephone in here is haunted. It seems to be calling someone. What's it doing? This is really weird. I can even see it typing in the numbers. Alright, I'm going to have to try and sort this out. Just give me a second. Hang on. I don't know what's... I can't stop it. I really can't stop it. Oh no, who's it calling? Oh no. What do I do?
Hello.
Oh, okay. Well, I think the haunted telephone spooked him out a bit too much. I think he's gone. Well, anyway, sorry about that. I really couldn't stop that. I did try to... Well, you heard me scrambling around to try and stop that from happening. Somehow all of the mating calls started playing again as well. I don't know what's going on in the studio today. Won't happen next week, promise you that. Right, well, thanks again for tuning in. Do tune in next time, of course, every Thursday, 7:30 till 9, here on the Source FM. That's 96.1 FM, of course, or online as well. Just Google Source FM. You'll find the link to listen to that online. And also find our Facebook, Cornwall Science Sessions. You really know you want to. Well, I know you want to as well. Right, I'm going to finish with this tune. This is an absolutely awesome tune. So I was driving back down to Cornwall the other day, actually. Went to visit my parents up in the Midlands. And I was cruising through the service station, and I came across a Busted CD. Yes, Busted. The great artist behind What I Go to School For, which is awesome. But I picked up their new CD, or their newest CD, called Night Driver, and I found this absolutely banging track on it. So I'm going to play this here for you now, actually. This is awesome. Well, actually, which one shall I play? Yeah, this one is particularly good. All right, I'm going to play you this now. Fits in perfectly with our love and breakup theme for today. And of course, after this, that will be me finished. So thank you very much again. Thank you for everyone who featured on the show. Thanks to Paweł, thanks to Alice, and thanks to Tapas. Hear it again on Facebook if you want to. Right, that's me done. Check out this absolutely banging Busted number.